My apologies, guys, but this is taking a lot longer for me to kind of figure out how this is going to work than it should. So we're going to go through a few of the trends in one video and the rest of the trends in the other to make the rendering go a little bit faster. So first thing we're going to talk about is Zeph, but before we do that, let's remind you guys that the periodic tables were developed basically predominantly by two men. The first one, Mendeleev, atomic mass, and Moseley, giving us our modern day periodic table arranged by atomic number. Now, arranged by atomic number brings us to the effective nuclear charge, or Zeph. Zeph, Z effective is another way to say it, is actually the number of protons in an atom. So if I have an atom like carbon, it has 6 protons with a mass of 12. Those 6 protons are what are attracting the electrons to the nucleus. Now, in a carbon atom, you've actually got 2 different energy levels. And so if you have a nucleus, go to the next slide here. So if you have a nucleus and an electron on the outside, say in the 1s, and then you have a second electron, or a third electron rather, in the 2s, these electrons are actually going to repel each other. These two here are going to repel each other, which means that the pull of the nucleus on that electron is going to be a little bit less because something's kind of pushing it off. And so it's getting in the way, kind of lowering what that effective nuclear charge pull is. And that's really what Z effective or effective nuclear charge is. Now, effective nuclear charge increases to the right, and it increases as you go up. Now, in reality, it actually decreases as you go down, but that's all right. It increases in this way. It's a little bit different and difficult to describe, but that's okay. We'll get to some of those hard to understand concepts with Zeph a little bit later. But I do want to talk about some of the trends. So all the arrows that I'm going to draw represent increases. So it increases to the up and to the right. So here it is right here, showing it increases as it goes to the right. There are a few exceptions to effective nuclear charge that I have to mention. The first one is in between, like right here where I'm drawing in between the S and then where the P starts over on this side. So from beryllium to boron, there will be a decrease, because those S electrons a little closer to the nucleus will actually repel the P electrons. Now, why in reality that's not exactly what's happening for pre-AP right now, that's probably enough information. Don't want to confuse you guys too much, but you could say for our class that the S repels the P. Outside of that, there is another important exception right here, and that is right there in the middle. When we were drawing orbital diagrams to describe things to you, we had like 1 electron would go in each one of the bedrooms. And then when you add that other one, it's going to repel. So that value for oxygen will actually be a little bit lower than the value for nitrogen. On this slide, well, it's actually on the next slide, but that electron pair repulsion inside the same orbital is what we call a doubly occupied orbital. Those doubly occupied or half-filled orbitals that gain 1 more electron actually decrease in their value. Other places that you see is where inner energy levels push the outer exterior energy levels a little bit more. And so those towards the outside will experience more of that electron pair repulsion I was talking about earlier. So looking at these actual Zeph values, you can see we got hydrogen in the column 1, and then here's in column 2. We've gotten rid of all the D's here just for quick, discussion. But right there in between is the S's and the P's. So lithium, beryllium, and then boron. If you look at those 2 values, the boron value is just a little bit lower. Not a lot, but just a little bit. And that's that repulsion that I was talking about between the S's and the P's. If you look over here at the oxygen, look at nitrogen at 2.07 and then oxygen at 2.0. Right there is that doubly occupied orbital. As that electron enters a second electron in that orbital, it actually causes a little bit of repulsion and makes that nuclear charge a little bit less. So where this shows up is in pretty much all the other trends. So the pull of the nucleus is going to pull the electrons in and actually make things smaller. So the atomic radius trend is actually the opposite. So it increases, like I said, all these arrows are going to be increases. It increased to the left and it increases down. I meant to say increases. We've got some issues this evening. Increases to the left and it increases as it goes down. Now that's not true of all of them, but the general trend is that. You might see a little bit of a difference in the oxygen, nitrogen, a little bit of difference between like the boron, beryllium, but not really. For the most part, it's the same. I see that oxygen, nitrogen, actually there is the exception right there between them. But for the most part, it's going to increase to the left and increase down because that pull of the nuclear core is going to be weaker on those. So atomic radius is actually going to get larger to the left, larger to the. So these are going to be your biggest ones down here by francium, and your smallest ones are going to be up here by helium. Helium is actually the smallest atom. So here's just another thing showing you here. Increases this way, increases down, just like we were talking about. So atomic size, like I said, increases as you go down the group. They get larger and larger because going across a period, you're in the same energy level going across a period, like going from beryllium all the way over to fluorine. But if you go outside that, they're going to increase the number of shells and they're going to get larger and larger. So I'm going to stop there and I'm going to start a second video that talks about the rest of the trends. Sorry about this, guys. We're trying to make it work.